so much. Okay, so the paper that we have here is called CalixBoost, and basically it's a stock market predictor. The use case that we are using here to showcase our method is the New York Stock Exchange Index, the NYA. And in this paper, what we actually do is a combination of gradient boosting machines, Ensemble, to see how far we can push the accuracy. Right, we are from Singapore, NTU, which is a mouthful. Right, so the outline will be a quick introduction, and then the related work, our data collection and pre-processing process, the feature engineering that we do, the model that we have incorporated, the tuning, our training evaluation, and the results. So why do we chose to experiment with GBMs? Because we realize that there is this perception that, you know, GBMs are not so accurate, especially right now, deep learning models are all the rage. And the other reason is because it's kind of like the black box that we cannot explain the output from the GBM models. So our objective here is to apply the GBM models that we have proposed to just a New York Stock Exchange Index. In fact, for the same purpose, it can be a single stock index or a single stock quantity. It doesn't matter actually, as far as use case is concerned. And we are trying to see if this methodology is deep learning pipeline can be efficient and accurate. So the related work that our paper is based on is we look at a comparison between a recurrent neural network model, which also includes sentiment analysis, one of the paper in 2018, and the accuracy is about 67%, and the next paper at 2019, they push it to 78% with more feature engineering. And we look at the ensembles of weak learners like the GBM that we are using, and we are looking at whether we can push it further in terms of performance. So in terms of sentiment analysis and so on, we use the open source, the Vader, we'll talk about this later, which register about 96% sentiment classification accuracy. Then we have our GBM, where we incorporate the ROC, the receiver operating characteristic curve, to use it to trim the features that are more relevant. And to evaluate the importance of the features that we have, we adopted a more systematic approach using the Shapley values. So data collection wise, New York Stock Exchange Index, and again, we collect the data from January 2013 to May 2020. So it's a long data set, and the data that we have collected typically is from Yahoo Finance, just like Dr. Teng, and is high, low, closing, opening prices, and other available indices like intraday high, that we calculate the daily return, the differences, the amplitude, the exponential moving average, and so on. So we derive technical indicators from whatever we can collect from the Yahoo Finance data set. And instead of looking at news, which are much longer, as in Dr. Teng's case, we look at the Twitter posts, which are shorter. So we look at the posts from 20 influential financial political news. So we have CNBC, Bloomberg, and so on. And we actually included Donald Trump's tweets just to see what is the impact, if any, of his tweets on the financial market, especially the NYA. So we also have incorporated macroeconomic indicators from the US Federal Reserves, and these are things like the federal funds whether they are financial and non-financial commercial papers, the interest rate, the central bank loan rates, treasury bills, and so on. So these are the so-called quantitative indicators. For data pre-processing, because we have to collect and crawl the Twitter news, we use Vader for the sentiment analysis, and this is what we call, it's not a binary model, it actually is a 5-rule model and so on, and it will derive a score. So the dictionary is quite well done, as in all the lexical features are adapted from the Linguistic Inquiry and Word Count Dictionary, and it is meant to also, in a way, to support the social media posting. So social media lexicons like our LOL, WTF, the emojis, and so on, emoticons are all included. And in addition to improve its accuracy, they actually have a crowdsourced approach where people also manually label their sentiment valence. So the humans ratings is those outliers that is 2.5 sigma and above are removed. So these are, you can take a look at, these are the lexical features and the sentiment polarity, intensity, positive and negative. And the 5-rule workflow model, basically, they also take into account, you know, if you have exclamation marks, if you have capital letters, or if you have a marginally degree of emphasis on the words used. The polarity is the same, but the valence can be stronger or weaker. So it is, there's a word sensitivity involved. So the composite score, we normalize it to minus 0.05 to 0.05 so that we can use it for training. Feature engineering wise, I mentioned just now, we collected a lot of technical indicators from Yahoo Finance, from the Federal Reserves, and so on. So these are then further decomposed to a number of features to be fed to the learning networks. As far as our so-called look ahead is concerned, meaning that we actually take into account 60 days worth of data to predict the opening price of the NYX or the next day's New York Stock Exchange. So it's a total of 60 days look back window, because if we just, which is equivalent to 3 months, because if we take 1 month, it's just 20 days of data, which is too short for proper prediction. And for the, we actually have to scale our data so that the outliers do not have unduly high impact on our overall data. So the 25th percentile and 75th percentile onwards outliers are actually being scaled up. So in terms of features, we have so many features involved. We actually use a way of measuring its time consistency or temporal consistency. So we use the typical AUC, the receiver operating characteristic area under the ROC, to look at the score for all the different features that we are using. So here we just present the AUC score for the various indicators that we use. So, just a point of interest, if we look at Donald Trump, actually his tweets are not, that does not significantly affect NYA actually. And in terms of feature importance, we make use of the Shapley framework. So basically the Shapley framework measures the so-called marginal contribution of the features, given that the other features are taken into account. So there will be each feature is being added incrementally and then iterated, and they'll be combined to result in this figure here, the so-called Shapley values. And it can be positive or negative depending on the importance in either directions. So I'll show the Shapley values later in the results at the next slide. So our CalixBoost basically is an ensemble of 3 GBMs. So if we look at the SGBoost itself, you can see that the difference in the closing and opening price, CO and all that, these are the top features in terms of importance based on their Shapley values. And this is quite consistent even with the light GBM and the CalixBoost, all right? So this is how we try to systematically measure the feature importance, since we have so many features involved, and then we can weigh them accordingly when we feed them into the machines for training. So in terms of design, we basically create ensembles, and what we are saying is that if we have a collection of weak learners, we can actually make them become intelligent. So it is actually a sequence of models that they are being iteratively created to correct the mistakes of the previous model. So in this diagram on the left, we can see the classifier 1 actually, what is being noted is that there are 3 points being marked out, and we say that these are actually labeled wrongly predicted. So in the next iteration, this wrongly predicted data points gets a higher weight, so that their chances of being included in the data sets to be trained for the next classifier is higher. So this goes on, and then we arrive at the correct weight for each of the data sets in the final classifier. Then what we use here is the approach is the same, but we look at the gradient descent algorithm. That means we make use of the gradient to minimize the error when we train the GBMs. So the 3 GBMs we use, CalixBoost is the latest, 2019. XGBoost started in 2014. So this XGBoost is one of the pioneer works, and it gets improved along the way, whereby like GBM's characteristic is it is able to reduce high dimensional data sets into a smaller dimension. And so it makes the GBMs more scalable, because our data sets and the number of features that we have are really getting more and more. And CalixBoost improves the performance by being able to more efficiently categorize the features using a statistical method. So our proposed CalixBoost is basically an ensemble of the 3 GBMs. So we train 3 of them and get their optimal combination of weights to have an ensemble. So the weighting for the contribution of the 3 GBM is actually 70 for CalixBoost, 10% for light GBM, and 20% for XGBoost. So our methodology is we actually train each of them, and then we iterate them through a series of weight combinations from 0 to 1 in steps of 0.1. And then we get the weighted sum, so that we have their best optimal contribution of the 3 GBMs in our final CalixBoost ensemble predictor. For parameters tuning, as we can imagine, there are so many hyperparameters. So what we adopt here is, instead of try and error, we use the Bayesian optimization tuning to try and arrive at the so-called optimal set of hyperparameters. So in terms of evaluation, our data set ranges from 2013 all the way to 2020. And notably, we go up to May 2020. The reason being that the COVID is kind of in full from maybe March onwards, March 2020, when the COVID strikes. And so we want to look at the so-called black swan event, meaning that we have an unexpected event happening, that is the COVID, versus the normal happenings or normal events. So we have the normal and the so-called black swan data sets. So training-wise, we use 85%, validation 5%, and our test set is 5%. So for the 5%, we actually have the ground truth. So we try to predict from December to March to evaluate the accuracy of our predictor. And for the so-called black swan event, which is the COVID situation, is from March to May 2020. So why we included the black swan? We just want to see how robust or how well our proposed model can generalize to fit or to predict unexpected events. So the evaluation model, the parameters that we use are root mean square error, mean and absolute percentage error. Then for direction, sign change accuracy, this is where we can calculate the accuracy, and then the mean absolute error. And of course, our F1 score, precision, and recall. And to show that the results is not just a snapshot of the best result, we actually change the seed of the libraries that we use, and we repeat the experiments over 10 times and get the average. So we compared against the neural network method RNN GRU, and two of them with RNN boost and the individual Gbms. So this is a set of results that we have. So we can see that as far as our proposed CalixBoost is concerned, our accuracy is up to 84.88% in terms of the directional prediction, in terms of accuracy and the precision and the recall. This is for our normal test data set one, meaning the normal daily events. Then for the black swan events, well, we can still achieve about 78%. Of course, it is 6% or 7% down from the normal days of prediction, but it is still very high. So this actually shows that our proposed model is robust, and we can actually generalize it for black swan events, which the training data sets may not have captured. In fact, they would not have captured because it's an unforeseen event. So in conclusion, we yield better results than individual GBMs, and to a certain extent, when the two papers that we compared with sentiment analysis from social media and so on, we also do better. And we generalize well, and it's pretty robust for both normal and black swan predictions. So for future work, we have to look at whether we can optimize the model further, because it is a heavy model, whether we can find a cheaper way to train it. And of course, we can expand this prediction not just to an index, but it can be any individual stock or other applications. Right, that's all for my presentation. Thank you.